Alright, so in our last video we talked a little bit about how to sketch graphs, how to find x and y intercepts. So today I want to talk about symmetry, how to find graphs of circles, and then hopefully to do some application problems. We'll try to get through all three objectives. We'll see if that works. We'll see if we're able to do that. So, thusly. So our objectives today is to describe symmetry. Second goal is to graph circles. And lastly, I want to do applications. Okay? So we're still on section 1.1 of the book. Alright. So let's do a working definition of symmetry which we can work with. Definition of symmetry I like to use to define it. When you have same thing via a line, via a line. So let's stop there. So it's kind of like a mirror, so to speak. Which is equal symmetry, which is equal something. Something where you see exactly the same thing. So you see yourself in the mirror, or it's like you could split yourself in half and have exactly the same thing. Okay. Now, of course, this does not work with human body because, as you know, we're not 100% symmetrical. But let me give you some examples of symmetry. And in mathematics, we have three types of symmetry. We have symmetry with respect to x-axis, y-axis, and origin. So we have three types. We have x-axis, we have y-axis symmetry, and we have symmetry about the origin. So to give you an idea of what these look like, so to give you an idea of what these look like, something like this. Here we have symmetry with the x-axis. So here's our x-axis. So this is our type A. You can see. So this is type A. This is x-axis symmetry, what it looks like. Where you see exactly the same thing on the opposite side of the x-axis. And then for your y-axis symmetry, for y-axis symmetry, you have something different, like this. And this is my y-axis symmetry. Where you see exactly the same thing on the y-axis. You'll have to deal with my drawing. It's not really all that great, but I didn't major in arts, so what can I say? Then, lastly, we have origin symmetry. Which looks like this. You can't really tell, so this is the symmetry at the origin. Okay. So we have the three types of symmetry. Now, we use symmetry to help us graph, and this is a factor that we want to use before attempting to graph our function. We want to know symmetry. Before we graph the function. And why do we want to know the symmetry beforehand? Why do we want to know it beforehand? The reason we want to know it beforehand is because it will make our graphing easier. Symmetry means we'll have to do less work. Okay. And so we have a few tests for graphical symmetry, which are as follows. So the first one is for x-axis symmetry. So it's whenever the first coordinate, x, y, is on the graph, and when I have the opposite of y on the graph. Okay, so whenever x stays the same and you have the opposites of y on the graph, this is, so I'm going to put that in green color. x stays same. Opposite of y. Okay. And then for the x-axis, and then for y-axis symmetry, is whenever we have x, y, and the opposite of x and y stays the same. So don't get them confused. Just like the situation with x and y intercepts, as we learned in last video, for the symmetry of x, y changes. Y becomes the opposite. For symmetry of y-axis, the x-axis changes. Okay. And of course, lastly, is origin symmetry. Is whenever I have x, y, and I have the opposite of both x and y. Okay. And this one I have opposite of x and opposite of y. Alright, translating it in short, when we look at the quadrants, okay, which you guys should be familiar with, right? 1, 2, 3, 4. X is symmetrical with quadrants 1 and 4. This is Q1, Q4. This will be Q1, Q2. And this will be Q1, Q3. Okay? So on the quadrant, when you're looking at symmetry, it's going to be symmetrical with the x-axis when you see in quadrant 1 and quadrant 4, with the y-axis quadrant 1 and quadrant 2. Okay? And so now that I've yapped my mouth, let's talk about So now that I've yapped my mouth, let's use this symmetrical test. Okay. And so let's test. What symmetry does the graph x squared minus 3 have, if any symmetry at all? Okay. Now, you can use two ways to do this problem. We can use the algebraic test. Or we can use the graph test. Okay, either one works. So I'm going to show you both solutions in this situation. Now, solution A is easier because to do solution A, what I want to do is take negative. I'm going to take negative x and plug into the equation. So wherever I see x, I put a negative x. Okay. And if I get the same equation, it is symmetrical with the y-axis. Thusly, as such, I end up with y equals negative x squared minus 3. Negative anything squared inside the parentheses becomes positive. So we end up with the same equation. Therefore, the graph of y with the y-axis. Now, the other way to do this is the solution B. Is of course to choose points. Okay. So let's say for our x values, they're arbitrary, but the idea is to show symmetry. So we want to choose the same amount of numbers on one side as we do on the other. So let's choose negative 2, negative 1, 0, 1, and 2. Okay, the idea is to show symmetry. So if these values are exactly the same, then it will be no problem. And so recall the equation is y is x squared minus 3. So we just take in and plug in our numbers that we have to the equation. So this becomes y of negative 2, which is of course negative 2 squared minus 3. One minus 3, which is of course 1. Okay. And then nextly I have y of negative 1, which is of course negative 1 squared minus 3, which is negative 2. 0 becomes negative 3. If you haven't caught on, 1 will be negative 2. Y of 0 is 0 squared minus 3, which is negative 3. Y of 1 is 1 squared minus 3, which is negative 2. Y of 2 is going to be 2 squared minus 3, which is of course 1. So this will be minus 2, and this will be 1. And since these two are exactly the same, I can say it's symmetrical with respect to the y-axis. Because again, the opposite of x is the same. Okay. has the same value. So you can say symmetrical y-axis. Now, of course, you can visualize this. You can visualize it, you can graph it, but there is a more algebraic way to figure this out. Okay. -3. To 1. I can't really draw it perfectly, but that's okay. So we have 1, -2. So it looks something like that. It's not perfect, but it'll do. It's not perfect, but it'll do. But the idea is to show you that it's the same on this side and the same on the other side. Since I kind of made up my own scale, it doesn't look exactly perfect, but that's not the point. The idea is to show you the symmetry of the two sides. Okay? Now, this kind of thing is called even function when we talk about symmetry with the y-axis. Now, so the algebraic tests for symmetry are as follows. So for x-axis, I plug -y for y and get the same equation. For y-axis, I plug -x, x, and get the same equation. This is called even function. And then for the origin, I plug -x for x and -y for y and get the same equation. Okay. So let's do another example of symmetry. Let's do another example. So example 2. Determine the symmetry (3x minus y squared) equals 1. Okay. Now we do not need to solve this equation for y. Okay. We can leave it in what we call implicit form of equation. So we just want to show the symmetry for this. So to do that, easiest way to do it is, of course, we'll just start by plugging in negative. I don't want to sit and go through all the work to this, but if you can see that there's a square involved, you always want to start with your negative. You want to start with whatever side has a power to it. So in this case, I want to use the x-axis symmetry. So x because of the y squared. So we plug in negative y in this equation equals 1. Anything squared inside the parentheses is of course positive. So it's 3x minus y squared is 1, which is the same equation as the original. Therefore we say 3x minus y squared equals 1 is symmetrical with x-axis. Everybody follow the idea. We're just taking our negative y and we plug it in. Okay? Now I want to do circles. Circles are not that hard. So many of you remember from your algebra classes of many, many years ago. This famous equation. I have triangle. This is C, this is A, and this is B. I know that A squared plus B squared equals C squared, right? Pythagorean's theorem. If you remember this, all this. Pythagorean's theorem, and you remember this all. A circle has similar form of this equation. So I want to graph and show you what the circle looks like. Shape, let's get a circle. This is a lot easier to work with. Okay. A circle has certain properties to it. One of them is it has center. That's what I was looking for, the eraser. Here we go. Our center, like that. So one of them has a center, HK, and I could derive this for you, but why? So, as you know, a circle has exactly the same radius throughout the circle. It forms like that. Now, this circle is formed. This is xy. This is some point on the circle. So to determine what this point is, it forms triangle, like this. This is right triangle, by the way. So to figure out what the equation of circle is, as you know, you remember the distance formula. So radius of circle will equal square root of x minus h squared plus y minus k squared, square both sides, and then we get what we call equation of a circle. So the equation of circle, that symbol means circle, is going to be x minus h squared plus y minus k squared equals r squared, where hk is the center and r is the radius. Okay, this is a very important equation, so memorize it. And if you don't memorize it, you'll run into problems because I'm not giving it to you on any kind of exam. So now, the most obvious thing is if the center is 0, 0, that's what happens is that the circle becomes x squared plus y squared equals r squared, just like that famous Pythagorean theorem. So, which I'm sure you don't remember from your geometry class. So, but you've done so many examples, it just comes back to you. So this is kind of where it comes from. The Greeks were oddly enough working with the circle when they were coming up with the Pythagoreans. But that's another story for another day. So, let's do another example here to find equation of a circle. Let's see, find equation of the circle. With points, with center 3, 4, and the point on the circle 5, 6. Okay. So as a rule, so let's just use the equation of the circle that we have here. We're going to use this equation here. So we have x minus h squared plus y minus k squared equals r squared. And we have the point xy, which is this one. And we have the hk there, which is before. So this becomes 5 minus 3 squared plus y. So it is 6 minus 4 squared, r squared. So 5 minus 3 is 2, 2 squared is 4. 6 minus 4 is 2, 2 squared is also 4, is r squared. So r squared equals 8. Square root of 8. Square root of 8 or 2 square root of 2. Thusly, as such, the equation of the circle will become x minus 3 squared plus y minus 4 squared equals 8. So that's it. Like that. So everybody follow this idea. I do it a little bit different from the book. But that's okay, it's the same process. So, as a circle, let's do one more. Find equation of the circle. with 0.105 and center -1, -2. So once again, we use the equation. We use x minus h squared plus y minus k squared equals r squared. So x is 10 minus 1. Be very careful when you're doing that. But remember, the equation is minus. So it's minus a minus, which will become positive. And this will become 5 minus 2 squared equals r squared. And so this becomes 11 squared plus 7 squared is r squared. 11 squared is 121 plus 49, which is, of course, 170. Is equal to r squared. So therefore, the equation becomes x plus 1 squared plus y plus 2 squared is 170. Now to figure out how long I've been yapping my mouth. So we should be yapping right now. 37 minutes. Okay, we have time to finish everything else. Cool. So now we have applications of this kind of material that we've been learning. And so your book has this application on weight gain, but since I don't believe in such ideal weights, let's do one from let's do a geometry example, or an electronics example. Let's do this one. So we have an application. Okay. So for this problem, let's do the example. Kind of show you. In this situation, they give you the equations to work with. Okay. They say the resistance in ohms, which by the way is represented with a capital omega, of 100 feet of solid wire at 68 Fahrenheit degrees can be approximated by the equation y equals 10,770 divided by x squared minus 0.37, whatever it is, and then it says for all x's 5 less than equal x less than equal to 100. Okay, it says where x is diameter of the wires, in mils. This is called thousandths of an inch. And then we want to graph this equation. And so it says use a graphing utility to graph it and find the resistance when x equals 50. Okay. So for the graph, so for part A, which is the graph of the situation, we're going to use the symmetry rules that we learned. So since the x squared has the square, we're immediately going to use which test? Right, the test for the y. Test for the y-axis, obviously. Okay. We use the test for the y-axis. Very important. Okay. So we know it's symmetrical with respect to the y-axis in this situation, and we get the same equation. So the y-axis symmetry test. Now, you guys will have a graphing calculator. Using y-axis symmetry test, you can show that this happens to be true. Now, I want to open up my graphing situation again. Choose this one. We'll make this full screen. So we have the equation of y is equal to 10, 770. Your calculator does not recognize international notation. And because your calculator does not recognize international notation, it should learn it. Divide by x squared minus 0.37. Graph comes out like that. Now we need to adjust the scale. So I need to adjust the scale on the graph so that we can see it. Format, view, window. That as soon as we As soon as I adjust the scale, we'll be okay here. You'll have to live with this temporary distraction. There. Anyway, the graph is going to look okay. We're having some technical issues here. Okay. So this is our graph. I'm going to adjust the window. Coordinate system. No, not yet. Format. Have it. Oh, frame limits. Okay. So let's try x from 0 to 100 by a scale of 10. Let's try my graph 0 to 20,000 by a scale of 5,000. We should do it like that. So the graph looks a little bit like this. So you can kind of see the graph. This is showing us what the resistance is. Now, what you're seeing here is that the resistance is inversely proportional to the diameter of the material that we're considering. And that may not make any sense because you guys have taken a physics class, but we know about material that when we speak of the resistance, if there is more space for it to go through, right? So as this increases, the resistance decreases. And that should make sense. If you have a bigger wire, fatter wire, there's more space for things to go through, thus implying less room for resistance. So this is what your graph will look like. And then for the second situation, it's just a matter of plugging in numbers into the equation. So for part B, I just want to plug in 50 into this equation. So 50 gets plugged in right here. So gets plugged in. So we end up with y is equal to 10,700 divided by 50 squared minus 0.37. I'm sure none of you are able to do that in your head. And so we have a y graph. So we do y variable function y1 of 50, which gets us 3.398. 13 notes, which gets us 3.398. So we 10,770 divided by 2,500 minus 0.37. Very good. So we get our answer for this equation of y is equal to 3.938 in ohms. Okay. And then your book in this problem goes to a little bit more significant figures. I don't really give a rat's. This is math class, this is not physics class. So the need for you to be precise about such significant figures is not all that important. So, thusly as such, this concludes kind of our section and what we're doing. So now you should be able to do all problems in the book without an issue. Your book is 3.9 ohms, but that's okay. So, thusly, now that we've done this problem, you can do our homework for this section, which is to read the chapter first. The entire thing, by the way. Read pages 1 through 8. And then on secondly, I want you to do page 9, numbers 21. Since you did 1 through 20. Numbers 21 through 70 through 69, odds. And then I want you to try 73. As your application problem, we did 77 in class. I want you to do 73, 76. And then I want you to try number 81 in the book. So this is your homework, and you'll have fun with that. And so, good luck with your assignments